Alright, let's take a look at the two 3-dot problems in the Chapter 11 problem set. Part 1 has just kind of a lot of vector-heavy stuff. It's a lot of manual taking of cross products. So you're going to want to look back in Chapter 3 at that a little bit. But the Part 2 has two nice problems to wrap it up, 62 and 65, both 3-dot conservation of angular momentum problems. They are nice. I like them. This one involves a gymnast, or an aerialist, I guess, actually, who's making a quadruple somersault, landing, lasting a time t equals 1.87 seconds. For the first and last quarter revolution, he is in the extended orientation, showing here, I1. Rotational inertia I1 equals 19.9 kilogram meters squared around his center of mass. I didn't draw the dot, but it's there. During the rest of the flight, he's in a tight tuck with rotational inertia I2 equals 3.93 kilogram meters squared. So what must his angular speed omega 2 around his center of what must be his angular speed omega 2 during his center of around his center of mass during the tuck? Man, if only I had production values for this. All right. So, because we have two i's, we're also going to have two omegas. This is a conservation of angular momentum problem. Now you might be wondering, how do I know this is conservation of angular momentum? Well, I will tell you. I know it's conservation of angular momentum because there is spinning and because there is no external torque. In this case, the only force acting is gravity, and gravity alone is not going. I know we just did the precession, like the gyroscope example in class, but gravity alone is not going to create a torque, at least not when the axis is about the center of mass. That is kind of the key thing. So axis through center of mass, gravity equals no torque. So, how do we set up this problem? Well, we know that we have this revolution of 8 pi that takes 1.87 seconds. And I'm going to split it into a 7 pi revolution and a pi revolution. And that's going to be all of theta. And now I can say that this 7 pi is going to happen in some time omega 2t, 2, and this pi is going to happen in some time omega 1 t1, with the condition that t1 plus t2 equals t. So that was awkward. Let's just open that up again, ignoring this terribly awkward moment. Alright, turns out this is going to be my ticket out of here, because I can just as easily have said that T1 is equal to 7 pi, nope, not 7 pi, I've tricked myself, just pi over omega 1, and T2 is equal to 7 pi over omega 2, because, yeah, that shouldn't be too bad. Angular velocity times time equals angular displacement. This means that if I plug that in there, well, yeah, you know what, I've probably given too much away already. This is meant to just tell you how to start the problem. You can probably figure it out from there, I'm hoping. Point is, oh, no you can't. Right. Why is this conservation of angular momentum? This is the non-angular momentum part. Conservation of angular momentum, though, tells us that I1 omega 1 is equal to I2 omega 2. So why is that helpful? Well, if you were to look at this, we're going to have this pesky factor of omega 1 floating around. And no one wants to know about it, and no one does know about it. However, we can put omega 1 in terms of omega 2, which we do care about. Omega 2 is this wonderful thing. Everybody loves omega 2. It's great. It's, whatever. So hopefully that gives you some place to get started. Definitely gives you some place to get started. Hopefully gives you some sense of direction with 62. Now let's come to 65. 65 is actually this is, I think, a close to AP problem. It brings together a couple different ideas. It involves putty, which is a popular thing. I think there's an AP problem that actually looks almost identical to this. Basic premise is we have a wad of putty, showing here. Wet putty, they say, I think. I'm not terribly certain if that's actually relevant. But it strikes two balls that are attached to the ends of a thin rod. And they tell us actually that the length of the rod, which will probably be useful in a second or two, is 50 centimeters or 0.5 meters. So, what happens? Putty strikes rod, rod will begin to spin. This is one of these great cases where this spinning is definitely angular momentum. That makes good sense. However, the weird thing is that this putty also has angular momentum. We're going to measure it about this axis. So this means that our initial angular momentum is going to be right before it strikes. We're going to say that, we've got RMV sine theta. We're going to take theta to basically be 90, so this is 1. And so there's our initial angular momentum. Our final angular momentum, then, will be I omega. And we need to get I, which, since we have, effectively point masses, we're going to sum up all of the little bits and pieces. And the things we have to worry about are the two balls and the putty. And we know how far they are from the axis. It's a good old distance, L over 2, not to be confused with this L, which I realize now is probably confusing. Let's make this a capital L. Make life a little bit better, at least. So they ask you about this, then they ask you about the ratio of the kinetic energy of the system before and after. And then they ask you this cool bit where they ask, through what angle will the system rotate before it momentarily stops? So, there are two ways you can think about this. And this is where, this is the skill that we want to develop. So, when does it stop? We can think of this as a kinematics problem or a dynamics problem and kind of deal with it through, forces and maybe kind of acceleration. Or we can think of it as an energy problem. I'm going to encourage you to take energy in this route. Energy is usually going to be the neater thing. It's going to be a little less calcy, it's going to be a little less vectory, and a little more straightforward. And energy is just a really cool principle in general. So if we're asking when does it stop, we're basically asking the question is when does it not have kinetic energy? So the corollary to that is, well, what kind of energy will it have if it doesn't have kinetic energy? Well, as this spins, it's going to have, some changing amount of gravitational potential energy. And so as the gravitational potential energy changes, we can figure out that, it must be storing some energy in that, and thus it's going to be stopping at some point when, some height is balancing out this. So if you can figure out the height, you can figure out an angle. It's a little tricky, it's a little involved. I think it's a pretty good example of something that is AP-like. So this is a good problem to have for a workout. Anyway, hopefully this helps you get started on the homework when you ever get around to this, after the test and all, but something to think about.